Okay, so anyway.
I think it's 3 pillars with 2 neighbor rules, like
Okay.
neighbor and the nearest.
I think it's just nearest neighbor. I think, let's see whether we can, let's see what, okay, so this was 2007, 3 color, nearest neighbor. If I'm not mistaken, and am I getting this wrong? Am I already getting this wrong? I think it looks like that. And then it will be a random integer list of 0 to 2, let's say 500 of those, 400 steps, and then an array plot of that. Let's see if that's going to give something sensible, or if that's going to give complete garbage. Yeah, there we go. That's that rule. Okay, so let's take a look at whether this guy is a potential candidate for what we're talking about. And so it will be nice to be able to start the thing off from some simple initial conditions. So let's just imagine, I'm just going to guess, let's just imagine we could start an initial condition like that. Okay, that was completely boring. So, well, maybe we should do random initial conditions to begin with, and just see what happens in terms of the scaling of this thing, as we go to very large scales, because I think it's going to probably get kind of boring on very large scales. So let's take a look at this guy, and let's just for fun, let's do him at 5,000 by 4,000. Okay, so that might, that's interesting. I mean, so that's not completely, so this thing is still showing some signs of structure, if the thing would actually, so it's still showing, it's still not completely boring, even if we multiply by 10. So that's kind of interesting already. If we multiply by 10 the scale that we're operating on, it's still got some structure. And I'm going to save this file before I forget what's going on here. Let's see. Space coin 1. Okay. So I think to be able to see, so to be able to see much larger scales, we're going to have to start. So the ultimate, the coin size is 90,000 pixels, which is quite a lot. And 90,000 pixels squared is going to be how much? Okay, so that's a solid 8 gigabytes of 8 gigapixels. So we may not be able to get quite to that scale, but maybe we can get close to that. Now, I think Cellular Automaton has an option for for sampling only every other cell. So let's take a look at how that works. I think what we do here is we say, maybe we look at the documentation to know what we're talking about. Let us see here. So this should give us the way to tell initial conditions. Okay, steps T1 through T2 dx. Okay, so let's say this is steps 0 to 4,000 in steps of, let's say, 2. And then we'll say let's say, from 1 to 5,000 in steps of 2. So this should give us, I think, the thing that's been sampled. So we're kind of coarse graining this thing to, okay, wow. That is interesting. That it looks, okay, so let's coarse grain it by a factor of 8 in each direction, and let's see what it does. So this is kind of looking at it's kind of interesting that it doesn't actually just look completely like nothing. Okay, so that's coarse grained by a factor of 8. So now maybe we can go, well, let's see what we can do here. Let's go see if we can live dangerously. Let's try and multiply by, for example, this may be way too dangerous, but let's try and multiply by 4 each of those dimensions. Why did that come up so quickly? Why was that so quick? That was incredibly fast. Why was it so fast? This was, oh, no. Oh, maybe this needs to show times 4 there. Wow. Wow, this is really efficient. Well, so, okay, so this claims to be, if it isn't wrong, this claims to be the 8 times, actually, this is surprisingly, I'm surprised at how much structure this thing still seems to have, even when we're So this is now at 16,000. So we could actually get all the way, probably, given how fast that was, we could probably get all the way to an object that's 90,000 cells across. Let's see. So we have to go, well, let's just actually put it at 90,000 there, 90,000 there, and 90,000 here. And let's do this down by a factor of, let's say 40 or something. So this is now going to be the 40 times. Let's see if this works. Okay, all right, okay, fine. So that's what happened. People can see that. It's a little bit, why is my, okay. So this is kind of what, so it's a scale of 90,000, this is what it looks like. So there's still some structure, but it's definitely getting kind of boring. So our challenge, so the good news is that technically we're going to be able to compute the thing at the right size. Then the challenge is to see whether we can get something where there's actually structure, as opposed to, I mean, I'm really quite surprised that this thing has these tentacles that last so long. And in fact, we can probably work out the transient time for all those tentacles, and it'll probably be some, I don't know whether it's an exponential, a power law, whatever. But okay, so here we've still got something where if you zoomed in, you would see, lots of detail. So the question is, so one thing we might ask is, if we start off with a simple initial condition, when can we get something non-trivial here? So I guess what we need to do is just take this rule and find out for what initial conditions it shows non-trivial behavior. And one obvious way to do that is just to say integer digits n3. So and then just make a, I don't know, we don't have to go 400 steps, we can just go 100 steps. Well, actually, we just go 50 steps probably. And we'll just make a table of those, let's say for the first 30 initial conditions. Okay, so the first 30 initial conditions are all boring. They just give structures that just stay a fixed size. So we can go, well, let's just do 200 of these just to see whether we get anything that grows. No. So with this rule, basically, nothing grows, it always just dies out. So we probably need some code to go find out whether there is a structure that grows. So maybe we can just do that by looking at, well, in fact, one really simple way to do it, gosh, why is it so slow to scroll this? Here, let me close that up. So must have a lot of pixels inside there, or it must be interacting with our screen sharing stuff. Okay, so let's see. So what we can do here is if we just say this thing here, and we just say that for a particular value, let's say 11, and let's just say, show me the result for step 50. No, I want 2 of those. So this will hopefully just show me the result for step 50. Okay, so that has not grown. So we can now, if we just go through here and we just make a table of these, and we just say, okay, so n up to 1,000, let's say, and now we just say, and then we say length. Actually, we can just go ahead and say length of that. So this is just going to give us the size of the little thing. Okay, that's totally boring because I didn't do the right thing here. I should say length the first of that. So this is now going to give me the okay, so this basically didn't grow. That's a little odd. Let's see, what is the, oh, that's because I said integer digits of 11, which is kind of stupid. Okay, so this is showing us the size of the structure after n step, what did I, no, I got this completely wrong. Yeah, I mean, I just want to do this after like 40 steps here. Okay, so this is saying that basically none of these structures grow. The only reason they're getting bigger here is because we're looking at digits of a larger number. So that's completely boring. So let's see what happens if we go up to 10,000. It's still completely boring. So I have a bad feeling that this rule simply can't grow unless it has some background. Maybe what we should try to do is to see for this thing, okay, so maybe we should actually look at the rule. So let's say this is the rule, and okay, so this is a totalistic rule that says when the number of cells in the neighborhood is yeah, there's a question from the live stream about whether we need to specify a background. Oh yeah, you know what? We're doing something completely wrong here. Thank you to the person who pointed that out. Okay, so what we did here, which was completely wrong, was we were just telling it to evolve within that tiny region. Wow, what a stupid thing to do. Okay, so let's do this again. Oh, well, that's completely different. So what we were doing before was we were just saying evolve within that tiny region. So in fact, even with initial condition 2 here, we're already getting all kinds of structure. So okay, forget all that. That was all totally goofed up. So what we want here is the initial condition integer digits of, let's see, 2. Okay, let's take a look at this. Okay, so the claim would be that this, oh, well, that almost showed non-trivial behavior, but actually it only grew for a while and then it died out. So the question that we have is, do we have any initial condition for which this will not die out? And I mean, by the way, we're looking at just this one particular rule, which I have no reason to think is going to be particularly interesting, although I have to say I'm surprised that it didn't just become completely boring, because most of these rules do become completely boring when you go to when you scale them up by that kind of factor. But so I'm trying to find out whether we can get an initial condition here. So in fact, the thing that I was computing before isn't so silly. I can just say go 50 steps and see how big the thing has got at 50 steps. So let's see. Because that one only, okay, so go 50 steps here. And that's a certain one of these. And then say length of first of this, and that will get us, and so now make a table of those for n goes up to 20, for example. Okay, so this is now showing us how big the structure gets after 20 steps. So we can go ahead and do this for like 1,000 of these. And let's make a, well, let's just make a list line plot just to get some idea of what's going on here. Okay, well, the most relevant point here is that there's nothing that grows above size 30. So there's no initial condition here which is showing, well, actually, let's just check that. Line 24, we can say max of %24. Okay, so it didn't grow above size 30. Okay, so let's try just running this. Let's just try running a lot larger version of this. Let's call it size. Let's run 100,000 of these. And then we can just say, what's the max? How long that will take? Okay. Okay, so this thing just doesn't grow. And maybe we can try, let's try looking at it with a bound background which isn't a 0 here. That might give it a chance to grow even when it doesn't grow with a 0 background. So let's, yeah.
This with 50 steps. So it grows up to 35 if you only take first 50 steps.
You are right. Thank you. You're right. This is only taking 50 steps, so it might actually grow bigger than this. So let's take 200 steps here, and let's just see whether that. Aha. Okay. Well, so something grew bigger than. So let's say we need to find the position of the maximum. This is something I keep on wanting to do, and I thought we had introduced a function to find this. Let's see. Well, we can certainly find the position in that size thing of the thing that is 90. Okay, so there are a bunch of these. So let's take a look at one of those initial conditions, and let's see what it does. So this is that initial condition, and let's see, this is the code for that. So that initial condition, and let's say here we want to say integer digits, comma 3 of this thing here, and this should show us the whatever growth happened. Oh, interesting. Okay, so that one is still alive and well, and maybe there are even other ones that are alive and well. So let's try running that for a lot longer. So let's try where are we here? So instead of 400 steps, let's try 2,000 steps. Let's see what it's doing. Humpty humph. Okay, well, it'll be interesting to see what it does eventually. I mean, that it's as a well, let's see what it does. Let's see what the question is it going to? Actually, this is an interesting case. This is a nice little undecidability question. So is it going to die out or not? And let's see. Well, let's keep going. Let's say we go 10,000 steps. Ta-da! It didn't make it. So after about, interesting. So after a while, it just resolved. So this is kind of this is an interesting kind of computational thing. This might be a good example of undecidability in action, so to speak. It's like, what's this going to do? All right, so let's actually, with that in mind, I'm now curious what some of the earlier, well, let's see, for this, so this probably suggests that there are even earlier things in the list of, where was it? I've got my list someplace here. SZ is my list of sizes of things. So if I just take the first 200 of those, let's say, that will be the growth rates. So there are a lot that get to size 31. Okay, so the first one that gets to size 31 is the one with initial condition 2. And that one just dies out. That one dies out after a little while, right? So initial condition 2, let's see here. Let's just do it for 200 steps. Yeah, so that one just does that. So probably most of these 31s are just doing that. So let's take a look. Let's take a look. It's a somewhat coarse way to do it, but let's take a look at the first numbers that are bigger than any number that's come before. So who knows how to work that out in a list? We want the first entries that are bigger than anything that's come before. So I think if we say, well, let's see. We really want the positions of the things that are bigger than anything that came before them. So, okay, who can see how to write that piece of code? So we've got the size thing. Let's say take size, comma 200. We want to know which numbers here are what the positions are of things which are larger. So let's see, take largest. Well, one thing we can do, yeah, actually, here's the way to do it. Here's the way to do it. We just fold. Okay, I claim the following will work. If we say fold max over this, yeah, that will give us always the running maximum that we've got so far. So this should give us this. If we find the position where these things change, that will give us the positions at which. So this is going to tell us. Okay, so then we have to say. Now we can just do a split on this, I claim. And then, well, that would tell us what the, actually, sorry, the better idea is just to say, okay, so let's fold the whole thing, let's get the whole thing folded. And now that will give us the maximum so far. And now if we just say delete duplicates of that, that will give us the running totals maxima so far. And so what we want to say is first position in SC of each of those things. Okay, so that gives us the positions, the the first places where we get bigger creatures than we've ever had before. So now let's just take this, and we should just go for those things there. We should just map this over those. So let's flatten, let's copy this list down, flatten that list. And so that should give us, okay, there we go. So those are the things, those are the patterns, the distinct patterns, at least with respect to the sort of heuristic of size. And let's run them a little bit longer. Let's say we run them for 1,000 steps. Okay, so what we're seeing here is that was the one that we looked at before. And this one here, which number is that? This is very primitive. 1, 2, 3, 4, 5, 6, 7. Am I miscounting this? Why don't I just label them? Why don't I just say in here, plot label, arrow, hash. Okay, so that is number 4048. So this is telling us this one here, so let's try 4048. Okay. Oh, didn't make it. So that one after about 10,000 steps dies out. Okay, well, anyway, let's maybe go back to the original problem. So we've got this rule, and so far as we can tell, this rule is actually a really nice example. I've been looking for one of these for years, of a kind of sort of undecidability in action type rule. That is, what's it going to do? Can we find an initial condition which will continue to sort of flap around forever, or will they always die out? And I mean, we could just try some of these other ones for 10,000 steps. Well, let's just try each of these for 10,000 steps, and then we'll find out what happens here. That's really disappointing. All of them died. Well, actually, all of them except that one. Has that one died out? I think that was the one we looked at before. And that one has not died out after 10,000 steps, but we know it does die out after 100,000 steps. But all these other ones seem to die out even after 10,000 steps. So, well, let's see, did we find out? Let's see, did anybody remember whether that one, this one here, 1406, what happens to 1406 after, okay, so 1406 after 100,000 steps. 1406. Okay, so after 10,000 steps, it's still alive and well. After 40,000 steps, it died out. In fact, yeah. So 15,000 steps is its kind of lifespan. It's a remarkably long time for something that tiny. I mean, it's cogitated for a long time before it finally gives up. It's really quite unclear what this is going to do. This is a nice example of undecidability. I think the simplest one the one I've used for years is a 4-color rule. This is a simpler rule. All I have to remember is 2007. It's a good year.
Stephen, are
yeah.
you using undecidability and computational irreducibility as synonyms?
So the question I'm going to repeat, because the people that is computational irreducibility and undecidability synonymous? No, I'm being sloppy. The undecidable question would be, the undecidability would be, is there a procedure which, given the initial condition, like 1406, given that number, will tell me whether it dies out or not? That's the halting problem. That's the infinite time halting problem for this system. So we're asking, so this is sort of, we're seeing a practical case of that, because if we ask, what is the lifespan? Let's see how we can compute, just for fun. Let's see whether we can compute the lifespan. So the lifespan is until it becomes periodic. Let's think. In fact, the experiment we're going to do a little bit later was going to involve trying to recognize periodic things, but maybe we can see an easy way to do that. Who can think how to do that? I think this would be, this would be fine transient repeat. That's That's the function. Now, whether that will work at a reasonable speed, let's see. Oh, okay. All right, so if we apply find transient repeat to, let's see what it does. Let's see if we just can take it to this cellular automaton evolution. Well, we can live dangerously and try it with the whole big one here. Let's say we have to do 5 repeats there. Can it figure it out? Can it figure it out? Ah, very promising. Okay, so let's say length. Why is that taking forever? Oh, it crashed just as it was doing this. All right, let's try this again, but let's try not printing out the result this time. And now let's say, that is really weird. What is it doing here? So, well, let's try a smaller case. Let's try, what did we have before? We had the case of 2, which becomes repetitive after very little time. So let's try that. So we'll try this thing, and we'll try that, and we'll try integer 2, and let's do just 100 steps. Let's see what this does. Okay, so there, I see. So this is giving us, so if we now just find the lengths of each of those, what is that doing? Oh, length of that. Okay. It's a little weird that it's giving us a 0 there, because that doesn't seem right. So let's look at the results here of cellular automaton, 100 steps. So this should give us something which eventually repeats with some period. Oh, maybe it hasn't repeated yet. Let's find out what happens. We're confused here. So this, in this case, let's make an array plot of this. That looks like it's repeated. Oh, it just repeats with a fairly long period. Okay, so let's go to like 150 steps here. And now what we should be able to do is to use that function find transient repeat. So find transient repeat should give us, find transient repeat has a second argument, which I need to find out what it is. It is, oh, I see, where the elements of repeat occur successfully at least n times. Okay, so that's basically saying we want at least n repeats. So let's say we want 5 repeats here. And now we should get a result which gives us the transient and the repeats. So let's just ask for the lengths of each of those things. Oh, great, there it is. Okay, so that's saying that it goes 63 steps and then it repeats with period 13. Okay, so now let's take a look at some of these others, because those ones will have long transients, and I might want to start a new notebook here because I think we're saving these giant cellular automaton evolutions in here. Let me go back up here to where I had that big list of, yes, there's my big list. I'm going to start a new notebook here and use, oh, come on. And use that big list of things there. Let's start a new notebook. I had it at 150% here. Okay, let's see. This was spacecoin 02. Okay, and now this is, so now for each of these, I want to figure out the corresponding find transient repeat type thing. So for each of these, the claim was that most of them, okay, so here, instead of an array plot, I want to say length / find transient repeat of that. And I want to, let's say five of those. And now for each of these, I want to take that and I want to map that onto this list here of our interesting cases. Okay, all right, so what this is telling us is, so there seems to be a period 13 motif that's going on here. What this is telling us is that most of those, so with the exception of this one, 10,001, which doesn't have a repeat, all the other ones have already died out, and this gives their lifespan. So in fact, it might be interesting to just go through and look as a function, since this length of fine transient repeat thing seems to be working fine, let's just go through and plot essentially the lifespan. So let's say 100 digits of n here. And let's, maybe we can just do that for, well, let's see. No, 10,000 steps is what we're going to need because there are things up there that, okay, so let's say this, and let's make a table of those for n goes up to, let's say, 1,000. This is a kind of a small computer, but let's see what we get here. So this is going to give us, hopefully, the lifespans, basically. This is kind of this is the halting problem in action. So the question is, how long does it take? You know, if we had a program, so the question is, can we write a program that will just tell us, given the initial condition, how long it's going to take to halt? And you know, this is doing it by the sort of computationally irreducible approach of just you run each step and see what happens. But gosh, this is taking forever. You know what I should have done? Do I want to just keep this going, or do I want to well, let's see.
I'm doing a lot of extra work here, because even for rules that die out quickly, we can do in 10,000 steps.
Yes, I know. That's kind of stupid. Well, anyway, we got the result now. So, okay, so let's take a look here at, let's just look. So we know all of these will have actually, so if we look at the last element of each here, oops, then, and we just say count, counts of last element of line 9. Okay, so it's always either becomes periodic with period 1 or it becomes periodic with period 13. Okay, so now we get to see what are the halting times. I mean, even that, it'd be interesting to see whether we can predict, but let's just look at the halting times. So the first of %9, so this is the list of halting times. So let's take a look. Let's do a list line plot of this. It's going to be a mess, I think. Okay, that's a mess. Actually, what's interesting about that picture is that there are definite halting times. There are definite bands of halting times. So if we make a histogram of line 12, okay, that's kind of interesting. So that says that there's either a creature that lives for about 60 steps, or there's a creature that lives for 100 and something steps. Or so actually, this relates to another thing that I really wanted to do. So this is another project. So we're slightly segueing here, but another thing that I was really curious about was, could you make a, you know, if you were going to do natural history on what happens in these systems? Well, so what that's telling us, okay, hold on. This is telling us that there are things that are either clustered around a lifespan of about, well, let's do this. How do we get what that lifespan is more precisely? Let's just do a histogram. Let's do these histograms just in size 1 bins. Okay, so that's interesting. So what that's telling us is so that's size 1 bin. So there's no absolutely precise. So what's probably happening is it's going into the structure which is flapping around for a while and then dying out. So it's not. And let's see if we can find what that structure is. So let's figure out the first. To get that structure, so there's 2 structures we want. There's one at around 110 and there's one at around 60. And so for that, I think what we want to do is to find the first example. Okay, so there's already here at case 2. Okay, so what we're wanting is there's one at case 2 and there's one at case that 116 there. So let us find the first position in %. It's always very bad to use % whatever, because it'll all go away when the notebook goes away, but I'm being sloppy here. But okay, so that's at 2, and then the next one was 115, I think, and that was at 146. Was it 115? Let's take a look. The first number, no, it was 116, was the first number that we saw that was in the range of that second peak. Okay, so 1, 2, and 71. So those might be the characteristics. So let's take a look here. Let's just get a picture there. And over here, let's say, okay, so that was 2 and 71. Okay, so the 2 case of 2, we don't have to go to 10,000 steps. We can just go to 1,000 steps, I think. So this is one motif. Yeah, okay, we just have to go to, that's it. There we actually only have to go to 100 steps. Okay, so that's one motif for a structure that dies out. And another motif is the thing that happens at position 71, which we need to go to like 150 steps to see. Okay, so that's the second motif. So what's kind of interesting there is this motif, I don't know what we should call it, if we were doing natural history and that we saw that as a sort of a frill pattern on a lizard or something, we would no doubt give it some Latin name. But I don't know what we should call that. I mean, but so basically what's happening is it's feeding into that same structure and then dying out. So it's got a little bit of extra twiddliness there, and then it's dying out. All right, but we should return. Well, this is interesting in its own right because it's just kind of a nice example of kind of what that's saying is that the morphology of these structures is we've got this one thing that dies out. We seem to have another one around here that's probably a simpler version of just the same structure. I mean, that sort of everything is dying out with that same structure. I mean, I'm also now curious what the we've seen structures here. Let's take a look. Have we seen any structure that propagates across the page? Or have we only seen structures that flap around a lot and then die out? We've never seen a glider here. We've only ever seen things that have this kind of, flapping around and then dying out. We've never seen something that systematically moves across the page, which is kind of surprising that doesn't exist here, if indeed it doesn't exist. So that makes me super curious whether, well, okay, our original problem, though, which was to get something which showed interesting structure on all scales, we've actually, this is not a terrible example because although it doesn't solve our problem of making a nice circular coin, it does have the feature that it still seems to be doing things. As I say, it still seems to be doing things on pretty much all scales. Now, one question is, can we find a glider? Can we find a propagating structure? I remember that in the NKS book that I had a procedure for finding these gliders. Let me see, where was it? I think here, these really big gliders, I had some systematic, what do you mean there are no notes for that page? How can there be no notes for that page? That's really weird. That seems like a bug in the online version of the book. No, maybe not. Maybe this is, maybe I have a different, okay. Maybe I discussed this in a different place in the book, but I certainly remember that there is a way of computing. So these structures, there is a, there is a procedure for computing whether there exists a structure. I think what would be the humph. Let's see. Okay. Well, this will do it. Oh gosh, this is basically you're building finite state machines of a certain size. Humph. Okay, well, this is maybe too complicated to do right now, but there's a procedure for finding out, does there exist a given a particular period of glider, like the thing is moving, one step to the right every step. There is a procedure for figuring out whether there exists anything of any size which has that characteristic. But I want to come back. Okay, so here, well, we got a nice example of a of kind of undersidability in action, partly because we know now that in here, let's see, in this case, we had found, what was the result? Yeah, here we've only got 10,000 steps, but what we know is that there exist initial conditions which will not stabilize for 10,000. In fact, we've got the example there, which didn't stabilize for 10,000 steps, but it does stabilize around 15,000 steps. So that's kind of showing us that's, if we were doing sort of, if we're trying to find, if we're solving the halting problem, we've got a case where it takes 15,000 steps to decide whether it's going to halt or not. And in all cases that we've seen so far, in most definitions of halting, it would be considered to halt, although the period 13 thing might be considered to be an infinite loop. My friend Nova on the live stream is saying that this thing is like a totem pole. I'm not quite sure what to conclude from that. But okay, maybe we should come back to the original question. And I don't know whether we have what we've seen here, the question is, do we have a strategy for finding, if we just look at, let's look at the original question for a second, which was given, can we, well, so here's an example of how we would address the original question of whether we can get a structure, something with structure on all scales. So let's imagine that we have something like this, and we are looking at, let's just imagine that we have an initial condition that's just a single 2. Oops. And we have 200 steps, and let's say 100 steps all. Now, what I was thinking about doing, how many totalistic cellular automata are there? Of 3-color totalistic cellular automata are there? There must be, let's see, if we look at the rule there, it must be that the total in the neighborhood, it's 3 things in the neighborhood, so the maximum size is 2 times 3, which is 6, so 0 to 6. So that means that there are 7 things, and each one has 3, so there are 3 to the 7. So it looks like there are 2187 rules altogether. So that's a modest number. So we can just go through and basically say, for each rule n, and let's say plot label n, so we don't have one that, okay, so for each of those rules, let's just go through table n 02186. And let's just, for the sake of actually seeing what's happening here, let's say monitor that, monitor it with respect to n. And okay, this is a little bit boring, but it's not going to take too long. So, okay, now it just has to display them, which might take a little while. And this should give us, there we go. Okay, so this is a, gosh, I used to do this so many times working on the NKS book. This is kind of an identity parade of cellular automaton rules, asking, are there any interesting ones? And so there are a lot of fractal ones. That one is probably too dense. Let's just take a look. Okay, so 63 has some interesting action going on. Now, usually, actually, what I've often done is I've often made these into buttons, so I can just press the button. As it is, I might have to do the really Neanderthal thing of having a separate window and typing. Let's do the really Neanderthal thing. And just typing in, I should have made these into separate buttons, but I didn't. Okay, so let's poke that window up above there. 63 is possibly interesting. Okay, what else is interesting here? 88, maybe. It's got that weird background, which is sort of ugly, but maybe it'll be interesting. And let's see, might be some others here. That one might be interesting, 113. Sometimes ones that look like that are interesting.
Steve,
yeah.
how do you decide which one is interesting?
Well, if it's a nested pattern like that, it's always going to be a nested pattern. In other words, the question is, can we as humans, this is sort of computational reducibility in action. Can we as humans figure out what these things are going to do? And if it's a nested pattern, it's a nested pattern. Game is over. Whereas something like that, we're not sure what that's going to do. Let's just go looking down. That one will have an interesting border, but I don't think it's going to do anything interesting internally. Let's look at 149 might be interesting. And in a minute, we'll just look and see how good our intuition was about what might be interesting. See, something like this, it's going to look like Rule 30 all the way down, so to speak. It's just going to be a big, it's not going to have any internal structure. Rule 173 there looks like it's a copy of one of the others, but we can note it down. Okay, let's just do a quick scan through here. Okay, 200 might be interesting. Unfortunately, some of these ones, it's a little hard to see what's going on because they have a background that alternates. Okay, that's just a nested one, but has that one, 223, might be interesting. I've seen ones that have those sort of scarring patterns in them that turn out to be interesting. Boy, this is a bizarre business. I mean, the fact that one even knows what, okay, 262 might be interesting. I've clearly spent too long. I think I used up, there's a part of the brain called the fusiform gyrus that is supposed to be used for face recognition. And I think I burnt one of those up looking at these things. Because I can't do faces, I can only do these guys. Oh, that one, 382, that one might be interesting. 382 and 383 both might be interesting. 382, 383. Okay, and we're going to stop going through these in a minute, except that I just want to, I'm now always, I think there's that 412 one is a copy of some other ones. So let's just keep going for a bit. If anybody notices something, let me know. Okay, there's a bunch of nested guys there. That's, again, I'm pretty sure these are copies, 559, 565. I'm pretty sure those are rules that are emulating each other. That's 589. That one might be interesting. Whenever you see something that doesn't show uniform external growth, it can turn out to be interesting. 5625, that one's definitely interesting. Well, he says definitely interesting. 629, 630. And again, we're going to find out, many of these, which we thought were interesting, might actually turn out to be incredibly dull. Oh, that's an exotic one, 655 there. I mean, again, most of them, ones like that are sometimes interesting, although they often end up just, there's an awful lot of nested patterns here. I mean, my friend Benoit Mandelbrot, who thought that in a rather paranoid way, thought that the whole NKS business would squash all interest in fractals. I always was telling him that that's not the case. And you can see here that there's no lack of fractals. There's fractals all over the place here. All right, quick scan down these. I'm gonna just accelerate here. And well, let's go. I just want to look for anything that really looks extremely exciting. Okay, 905 and 890. Well, actually, I don't want to do this because I'm going to end up missing ones. So let's just look at the guys that I already picked out. Now I'm just going to scan through here, and probably there's some really exciting ones that I've missed, and that, oh, look at that, 1384. I think 1384 looks fun too. All right. Okay, we're probably missing the most exciting of all in that big long list there, but and I think I said 1384 as well was also an interesting one. Okay, let's take a look here, and let's go ahead and for all of those, let us just run this with those rules, and instead of just 100 steps, let's say run them for 1,000 steps. Let's see here. We don't want to monitor, we want to do that. We don't want the table, we want to do that. And we want to do this. And let's see what happens. Okay, so, all right. Well, some winners, some losers. Some that turned out to be quite interesting and some that are completely boring. So if we can see these, so I would say the ones that look interesting for our purposes, for our space coiny purposes, 262 is looking kind of interesting. Other than that, I don't really see much here. I think these are all, they don't really seem to have a lot of structure. Well, at size 1,000, they seem to have okay, so that one is a possible interesting guy. So let's just take a look at 262 at even larger scale and see what.
Did not have 184 in the list.
What's
That
that?
was the most interesting one.
Yeah. Okay. All right. Let's just try that one. 1384. It may not be. Blah. Blah. Just a pile of gunk inside. Let's try it. Let's try it at size 2000 just to see whether anything more exciting happens. Nope. It's just gunk. See, some part of our universe may be like this too. Just some pile of gunk. We like to think that we're on the, that in the analogy of us, that we're one of the structures that's more exciting here. All right, let's try 262 at a larger scale. 262. Okay, oops, that was at size 2000, so that was already, well, it's still not completely uninteresting, but let's do the following. Let's sample it every 2 steps, because it's going to be more. Let's sample it every 2 steps in space and every 2 steps in time, because I think it's going to get more. Let's see. So I want 2000. So in time, I want to go from 0 to 2000 in steps of 2. And in space, I want to go from minus 2000 to plus 2000 in steps of 2. Let's see what that looks like. And let's forget about the, let's say 262 here. So that's going to get rid of that nasty background that makes it hard to see what's going on. Okay, not that exciting. Okay. Well, let's see what it does if we go longer. So that's at 2000 steps. So let's go ahead and let's live a little bit dangerously. Let's go to 8000 steps, and let's downsample here by a factor of 4. Just to have a slightly smaller graphic. Oh, well, not terribly exciting. That's going to, because by the time we get that on a little coin, it's going to, although it is showing, I mean, those weird long scars are sort of interesting. Let's see what happens if we go even a bit larger. Let's go to 20,000 steps, and let's go here to let's go there to like 10, downsampling by a factor of 10. Pretty soon, what one's going to find out, the really shocking thing would be you generate one of these pictures, and there's a picture of a cat or something. Then you know that the universe is kind of coming to an end or something. But okay, so there is some definite structure there. This thing is not completely structureless, but it's still not. Let's just try the one that seemed, 1384 was becoming boring. But so the question is, can we recognize, so that we were sort of doing a visual search here. And I think what we're seeing is these ones that they have to have quite a bit of sparsity. And we can try another one here just to get some intuition, like 630. Let's try 630 there. And just to get intuition about what happens. I think 630, okay, that's it's kind of completely boring. It's just a pile of Rule 30-like stuff. But so, okay, so that just for the sake of, here we go. Let's just look through a few of these others and just see whether we get. So the one that we thought was interesting was 262, and that turned out to be not completely boring. 262. Let's see what that one looked like here. There it is. So that had sort of some slightly large-scale structures in it. So what we want to kind of look for is things with slightly large-scale structure. And it's kind of hard to tell sometimes, because sometimes when you go to larger scales, things which looked like they were just completely uniform here end up getting interesting. So I think just do a quick scan through here. And again, I think we'd gotten 625 turned out to be boring. 630 turned out to be boring. Let's see. Let's just make our little handy list up here. this is I mean, in principle, we should be able to use some machine learning method to figure out. I mean, the right way to extend what we're doing here is to select ones we think are interesting, then train a machine learning classifier to do that. Okay, let's look at 791. 791, I predict, is probably uninteresting. It's probably going to turn into a nested pattern after a while, but it just might do something more interesting. And 797, I'm telling you, this is one of the more bizarre. 835 has some large-scale structure. I mean, undoubtedly, there's a way to recognize these things automatically, but I'm okay. 905 might be interesting. Okay, let's see if we can get that one. Is almost certainly just nested, unless it blows up somewhere. No, I'm pretty sure it's just nested. I'm not absolutely certain. Let's put it down on our list. Oh, 946. It's kind of lively. Some stuff here. 1020. This is one of the more peculiar. Well, one can view this as a form of art. It's like taking photographs of different kinds of whatevers. It's like which of these is going to make a good picture. For some reason, 1179 looks to me like it might be interesting because it has those somewhat large triangles, and that's unusual. Okay, let's see. 1291. All right, we're about to be done with whatever we can do here. 291. Quick. Look through these. 1384 we already looked at. 1521. That's probably going to be very similar to the one we already looked at. The 1635 is a famous one. I've looked at 1635 before. See, the issue is what is going to be interesting on a length scale of order 90,000 pixels. Okay, more of these. Okay. Sorry, this is kind of dull at some level. It's only interesting if you're into. Okay, come on, we're almost there. That was our 2007 one. Okay, 2027 I think has a possibility. 2036 I predict is probably not that exciting. 2043, and we're almost done here. 2047. And they'll get boring at the end. Okay, so we've got another list of candidates. Let's just take a look at what those do. The exciting thing is if we actually find something cool here. And as I say, if we find one of these that emerges with a picture of a cat in the middle of it, it's or something which spells out, game over or some such other thing. Okay, let's take a look at these. All right. Oh, okay. So that first one was a quite attractive but nested pattern. That's another nested pattern. 163. Oh, that's interesting. 1662 has a rather lively kind of. Okay, so 1662 is sort of interesting there. Let's try taking a look. Okay, I think the only one with promise here is 1662. So let's look at our giant 20,000 cell version of this. And let's just look at 1662. Boring. Okay, 1635 is one of my all-time favorites, I think. I think of those big pictures of it in the book. But let's take a look at it on this. Oh, wow. it just dies out after. So it has. Did I get it right? 1635. So let's look at it on a slightly smaller scale. It's maybe if we try a different initial condition here. Let's try like 212, for example. Oh, it lasts a lot longer, but it's still very. Although it has big wings, so to speak, it's still only got action in a small region there. So I think we're running out of time here. But so what do we conclude from this? Well, we conclude we have not found a great rule for this coin. We've concluded that we've got some interesting. I mean, what we really want is a rule that. For 90,000 steps. I mean, I suppose, in some sense, in some poetic sense, that thing we found that dies out after 10,000 steps, one could imagine if we could find something, I'm sure if we go longer in that rule, we'll find something that dies out after only, after 100,000 steps or more. And it's kind of a, if you want to have a piece of poetry, yeah, this is good. This is the analog of that poem Ozymandias that I quoted in the post about there's this famous poem by Shelley about how some traveler from an antique land, he sees this giant broken statue, and the statue has, and it's the statue was of some great ruler of the past, I think based on Ramesses II, and the inscription is "Look on my works, ye mighty, and despair." And of course, there's a statue in the middle of the desert. The works are all gone, and I suppose that the analog of that for these is you put on this coin this cellular automaton evolution, which just a little bit beyond the coin, if you were to run it, would die out. And that's kind of we could consider it the Ozymandias coin. Actually, that has a certain artistic appeal to it, I have to say. I don't know if that's so if we were going to do that, then what we would do is just find an instance of this thing. Well, it's kind of artistically, that's not going to work that well, because on the coin is a circular thing. So, and this is a big, long vertical thing. But I think that would be I think maybe that's the right approach. And I mean, it's kind of like be impressed by the computational effort put into this coin. We had to actually find something that would have this characteristic that it survives for the life, for the coin, and then dies out. And maybe that's, and these particular things seem to have a decent amount of structure that goes on for a long time here. Anyway, okay, so.
Do you want to print them just like this, or you want to go radially?
Okay, so the suggestion here is, could we print them radially in some way? Well, that's an interesting idea.
You can put them in the spiral.
Oh, wow. You just made it.
Well,
Wow.
this is random, but something like that.
You mean that every successive step is further out from the center?
Yeah, but we have to make sure that it's perfect. Triangle.
Yes. Okay. So what you're suggesting is that's a very interesting idea, because that, I mean, insofar as if this thing had, I mean, one issue with that is it's going to get much sparser as you go out towards the edge, because this thing isn't growing very much. It doesn't have very many more cells, and you would need to have. So if the thing grew, I mean, I've never really looked at that. If you take like Rule 30 and you grow it out from the center, it will then have a roughly. Am I being confused here? The circumference is, yeah, you'll be able to. At the nth step, it has 2n plus 1. The pattern is of size 2n plus 1. So at the nth step, you will have the same radial. Each cell will have the same angular, right? Because the circumference scales up like r, right? So it's like if you'd say t, then each cell will have the same angular. In fact, okay. Well, in fact, now I'm curious. Let's just do the obvious thing. So we can presumably use list polar plot to do this. Is that right? List. If we have list polar plot should plots points equally spaced in angle at radii r sub 1. So I claim what we should be able to do here, equally spaced an angle at, so if we say cellular automaton of rule 30, for example, and we go, let's say, let's just only go 30 steps, and then we go, let's find the position of all the ones in this, okay? And that should give us, for each radial, distance out, it gives us at what angular positions, right? So how does list polar plot work? So list polar plot, okay, so we give a theta and we give an r. So for each one, yeah, in fact, we just have to, yeah, in fact, this is probably going to be exactly the right way around. So we have an r here, which is the, and we give a theta. So at each distance out, so what we have to do is divide by, we're trying to get the angles corresponding to the, so each one of these at I think what we want to do here is to say map indexed. Okay, who can figure out what this is? So what we're trying to do is no, actually it's just a map, I think, of, so we're taking the first element. The first element tells us the time step, right? The second element tells us, first element is the time step, and the second element tells us the radial position, right? And bizarrely, this is, we might want to subtract 30 from those radial positions because that, or 31 actually, because that will then give us relative to a center line. So, okay, so I claim that this is hash sub 1, comma, hash sub 2 minus 31. And I do that onto this. And I claim that is going to give us, if I could get my brackets right, that's going to give us, okay, so that's giving us that. And now what I want to do is to take that second thing and I want to divide it by 2 pi. I want to say 2 pi times that divided by 2 times hash sub 1 plus 1, I claim. Okay, so let's see what that does. So that should give us that. And now let's say list polar plot of this. And ta-da, okay. So that claims to be, if we got it right, that claims to be the rule 30 pattern set up radially. So let's see what happens here. If we do rule 90, that looks like garbage. That doesn't look right at all. Okay, so what do we do wrong here? So what we're doing is for every, we are going out, what is the form here? This is, H1 is theta R. Oh, big problem here. We've got the ordering wrong. Theta R. Okay. Oh, that's kind of fun. That's definitely fun. Let's see what happens if we get rid of the minus 31. It probably won't make any difference. But it did. That's a little odd. So that was getting it. Well, let's see what happens if we go to 101. I go to 100 steps here. Wow, that's pretty wild. It's kind of nice looking, actually. Okay, so that claims to be rule 90 for 100 steps done radially. I mean, do we think this is actually correct? Maybe we should read the code a bit more carefully. Let's look at rule 30 then. Well, let's look at rule 150, see what that does. Kind of interesting. Okay, who can tell me if this code is right? So what we're doing is, for each, we're looking at the position of the ones, and for each of those positions is basically a time step and a horizontal position. The horizontal position is relative to this array. By subtracting the 101, I'm centering it so that the initial one is in the middle. And then what I'm saying is, get me an angle that goes from, oh, no, this isn't right. This isn't right. The minus 101 is wrong. because I want an angle that goes from 0 to, this angle should go from 0 to 2 pi. As that number goes from as the number goes from 1 to the size of the array, that angle should go, so it should be the case. Yeah, I think this is correct. So then what we are doing here, let's take a look at a very small case. Let us look at rule 254, which is just going to make, and let's look at it for 10 steps. And that was completely incomprehensible. Let's look at it for 100 steps. Wild. Well, I think what's happening, so there's a seam that's gone wrong here, probably because we're off by 1 somewhere. Where would we be off by 1? 2 pi divided by, we're off by 1. But I like the idea of these circular thingies. These are cool. Let's see. Let's save this away, space coin. Okay, so let's see. Okay, why do we have a seam there? So the theta values should be going from 1. Oh, I think I know the problem. I think there has to be a -1 there. No, that just gives us a bigger seam. Okay, so the theta the values of the first argument go from 1 to 2t plus 1, I believe. In other words, if we look at, in this case here, if we look at this, and we look at this for the case of 5 steps. Okay, so this is going from, the second argument is the maximum value of the second argument down here is, oh, it's -1 there. Well, okay, let's just try this. We're doing really weird Monte Carlo programming, but actually that worked. Okay, so for reasons we don't fully understand, because we don't really have our act properly together, okay, let's try rule 90 here. Ooh, well, I don't quite understand it, but we can see some nested structure. Let's try running it. Let's try running the thing a bit longer. Let's try running it for 200 steps, and let's get rid of the axes, because I think the axes are kind of irrelevant. Okay. I don't fully understand. I mean, there's a bit of spiraling going on there, which I don't really understand. Does anybody think they understand that? I mean, it looks like we're off somehow in the way that we're computing. I mean, if I try rule 60, which is which will only expand on one side. Weird. That's nice, though. That's a nice object. Wow. Okay, now we got to try 110, because that also is a one-sided expansion thing. Okay, I guess that's expanding on the other side, so we need the mirror reflection of rule 110. And we could get that by doing this. He says, hacking it slightly. We could reverse each row. There we go. That's kind of fun. Wow, that's kind of fun. The 2 people on the live stream are suggesting that rescale might be a useful function, and I agree with them. Yes, I do agree with them. That's a good idea. But let's try. This thing is wild enough. I'm just curious. It's using up a lot of bits here, but let's try and just do 500 steps here. Maybe. Okay. Let's see what a rule 110 coin would look like. And this, it's kind of fun. It's and now of course we have to try the rule 31. Although we think that's not going to be as exciting, because somehow, although maybe we just got blah. What a mess. let me remind myself what rescale does. I think it takes a list of, okay, it gives X okay, one of the coin creators here is asking whether these would make interesting diffraction patterns when interacting with a laser on the scale of one of these on scale of one of these things. Well, actually, of course, we have the technology to find that out. We just take a Fourier transform of these things. Let's see whether we can do that. I predict nothing. Well, I don't know whether something exciting is going to happen here. Okay, rescale gives it to run from over the range min to max. Yeah, so that is a better way to do what I was doing here. But I think we're getting it right. I think we've got the arithmetic right. This is, so rule 30, let's just look at a slightly longer run of rule. I'm just going to look at rule 45 because I have a suspicion that might. Why is it showing all that weird spiraling stuff? I don't understand that. I mean, it suggests we got something wrong here. Because why would it spiral like that? The thing has, oh, I know why it does that. It has a background of ones. It's not interesting. Never mind. Okay, so let's do rule 30 and let's do maybe 400 steps here. Let's just see whether we get anything exciting looking there. A little wild. I still don't really understand these spirals. So those things must correspond to a fixed angle on the edge of the pattern, somehow must map to a thing that is spiraling when we go to polar coordinates. Well, since this is a good idea, this polar coordinates thing is a good idea. Does anybody else have ideas about what to put on our space column?
So if you have this long cellular automaton going, right, very elongated evolution, you can just basically pack it into spiral.
Oh, yes, that's a good idea. Okay, so the suggestion is to spiral the long evolution. All right, well, let's just for the hell of it, let's try that. Okay, 15809. Okay, so this is, so this evolution was, let's see, what was, I think, our very longest one? Well, let's, what was our very longest one? We had one that we didn't, that went for 10,000 steps. I went for 15,000 steps. But 15809 goes for a lot of steps, so we can use that one.
2007.
What?
2007.
Yeah, but which initial condition?
Integer digits 1406.
Was that really long?
That was up to 15,000.
Okay, 1406. Okay, so let's just check that. Yeah, it's still alive and well. Okay, so now we got to take this guy and we got to see whether we can put that around a spiral. So how would we do that? So for each row here, what do we want to do? We want to say, we're going to make polar coordinates out of this. And what we want to say is, for every, well, we can make a simple spiral here by just taking, okay, so this is actually going to have positions of 1s and 2s. Position here of 1 or 2. And let's just do it in a simpler case just to make sure that we're not messing it up. Okay, so those are the positions. And so now, okay, what's the most naive thing we could do is to just say list polar plot. List polar plot of that. Okay, that's completely uninteresting, but I don't really know what it did. Actually, we could try, so each thing, oops, what did I do wrong? What I want is, help, there we go, this thing here, and I want to say reverse in each of those, and then a list polar plot of that. And that was boring. Okay, so there's probably a better way to do this. So what I'm trying to do is take the successive values. Oh gosh, how to do this? With successive time steps, I want the thing to be, oh yeah, I want to put a square root in. I need to put a square root of the number of time steps. So that's going to be the radius is the square root of the number of time steps. And then the theta value is the thing reduced mod something or other. Mm-hmm. So if it's 10,000 steps, what I want to do is, so it's, let's see, this function does theta r or r theta. This does theta r. So I want the thing reduced. I want the number of time steps. Let's see, the position is going to be a radial thing. The position within humph. Okay. I think I need help here. So I'm trying to map. Let's see what happens. If I say square root of hash 1, and I use that as the radial distance, and then I use as the theta value. Gosh, what do I want to do here? I think I might be able to use. No, you know what has to happen is for each of the ones that's present, well, here, it's this should generate just a spiral of some kind. Oh, great. Oh, no, I know why. Okay, if I run this a bit longer, I predict this is a spiral. Of a sort. And if we wanted to, we could make that a Fibonacci spiral, which would pack in a Fibonacci spiral with an angle of 137. Every circle has, so I claim the following thing. If you say table of, oh gosh, how do you do this? I think this is where we look at demonstrations project to go figure out what, and we look at phyllotaxis, because plants have figured this out a long time ago. And we look at phyllotaxis spirals here, and we say copy to clipboard. And we say yes. Okay, so this, yeah, right. So this is showing what happens as a function of the angle that you choose. And at 137 point whatever, what am I doing? Yeah. Am I losing my mind? What's the angle? What's the golden ratio angle? What's that? What, 137.5? That's what I thought it was, but this is a 137. Oh, okay. It goes through. It has a nice behavior there. There we go. So there, it's evenly packing the disks. That comes closest to evenly packing the disks in the plane. So this would be the way to. So if we could make a plot. So what you're suggesting is, in here there are spirals which form the, whatever they're called, peristiches or whatever those things are called in plants. Because each successive, so if we could plot, it's kind of an interesting problem to plot the plot a bunch of data values in. Okay, okay. It's a little complicated. Well, all right. Well, this was our. We actually had a different topic we were planning to also cover here. I don't know if that's realistic or whether we should. Did everybody who might have been interested in that second topic end up coming here?
It sounds nice.
Okay, fine. So anybody who's all right.
Yeah, we could go ahead and go into the live experiment.
straight into it using the same string.
Okay, fine. Well, all right, but I like to tie this off a little bit. I mean, this probably requires a bit more work, but I think we are. I like the idea of this Ozymandias coin. I think this is. Insofar as there's some communication, I don't know what one's communicating with a. I mean, it's a very bizarre business. It is, as I say, in my opinion, a somewhat philosophically doomed business. But it's at least interesting for humans if you have this thing and you say, you know, this is a thing which has a computation, and the question is what's going to happen in this computation, and this coin shows, as far as this coin shows something where it's sort of an undecidability coin in a sense. If we can find one of these where we just can't figure out what it's going to do after like millions of steps, that would be a cute example of something to have on this coin, particularly if it has a good visual appearance, and we might have a good idea with these polar plots for how to achieve that. So my suggestion is that we now segue to a different but somewhat related topic, actually, which, so new topic. Let's close out these notebooks, and I've probably got lots of, let's try and save that one, probably be huge. That's what you get when you have all these bits here, is the notebook is huge. But I think this is, I'm pretty happy with this direction. I think this is going to lead to a reasonable space coin pattern. Okay, so let's, we're going to segue to something different here. And what I wanted to segue to, okay, new topic.